Welcome to this lecture. Today we will see Balun. It is balanced to unbalanced. So, the acronyms of BAL, from balanced it is taken BAL and from unbalanced it is taken UN, that gives it Balun. Now, why the need Balun? What is the need of this Balun? Actually, a balanced antenna usually has at least one symmetry plane which can be grounded due to the symmetric structure. For example, a dipole antenna has a symmetry plane. You can see here that it has a symmetry plane which crosses the antenna axis at the feeding point, thereby dividing the antenna into two halves which are called two poles. If these two poles assume same current distribution, the radiation efficiency is maximum. The current should go in one direction and the same current should return to the other one. The goal is to feed the antenna in such a way that these two poles have exactly the same current distribution, that is the even symmetry. Now, this can be done, please look at the view graph, that if we put the source, here, now source generally we deal with balanced sources. Balanced sources means it has a positive as well as a negative polarity. So, the positive polarity will be connected to one half, the negative polarity with another. Balanced source, balanced antenna, no problem, and we can say that I1 is equal to I2. Obviously, you see this in reality always we call that this is I1 and this is I2, because in reality this I1 and I2 are never equal. Why? Because this whatever current is returning, because through the displacement current actually this current returning, but also both of these poles they are also getting some noise etc. So, that is called common mode current. But for radiation I need a differential mode current like this, that one current is going here, another current here. That means, there is a phase difference between them, 180-degree phase difference between these two currents. This should be there. So, this differential mode current only can radiate. So, this is desirable. Here we are assuming that noise is not there. So, if we can make this balanced source is driving this, then we have I1 and I2 and the antenna designer is happy. The next one is, but this is not practical. The earlier case that was not practical because I cannot put the source into the center of the antenna. Basically, source is at a distance. So, to do that there is a transmission medium or transmission line, and if we have two wires. So, I have a source, again a balanced source, I have a two wires and one of the wire is connected to the upper half and another wire is here. This is a balanced transmission line, two-wire transmission line is a balanced transmission line because current is going here in one direction, the same current is returning in the other direction. So, again this is now here since it is a distributed transmission line, here is a forward going current wave and backward going current wave, but that is giving that I1 and I2 same, obviously without noise. So, again the antenna designer is happy, but this is true for low frequencies. At high frequencies, what will happen if we do this antenna, this transmission line won't be able to take the power here, it will start radiating. So, what we do? We shield the antenna, and the best possible shield is we give it a coaxial thing. That means, two conductors, one is inside, another is outside. Now, how do we connect them to the thing? You see, obviously, you see this is a to prevent the radiation from the transmission line, what we do, there is an outer shield, and that outer shield is connected to the lower half, and the inner conductor that is taken out, the direct conductor is put here. Here you see the problem is that this lower half, this half, actually this you can do any half you can connect like this. This lower half, it is connected to the shield of the outer conductor. So, to the outer conductor it is loosely coupled, that means through that shield it is getting coupled, but this one is directly coupled. You can say that why we are connecting it to the shield, we can directly connect it to the conductor. If we do that, actually we are short circuiting the inner conductor and outer conductor. That means there will not be any current in the differential mode, current will be 0. That is why we cannot do that, and we do it like this, but this makes the whole thing that there is an extra impedance seen because of this loose coupling. There will be some impedance between this shield of the outer conductor and the ground, and some current will flow through that. That will make this I1 and I2 unbalanced, because they will not be now together. You see that these are same, but this there will be another current component I out through this outer one. So, this is the source of all problems in high frequency, because high frequency there was shield. So, in high frequency we need to have a coax type of thing, and that gives rise to this. Even at higher frequencies, if we have instead of coax, if we use waveguide, that is a single conductor. So, that will also suffer from something like this. Okay. So, you see that net effect of all these is this flow of I3 through the outer of the conductor. Here you can understand that I1 is one current going, I2 is that current returning, but then while it is getting connected, there is an extra impedance ZG, which is undesired, and that is giving this I3 thing. So, to the load, that is the free space load, it looks that the current one side is I1, another side is I2 minus I3. Even if we make I1 and I2 same, they won't be together. So, our job is to choke this I3. Actually, a balance job is to choke this I3. That it will do. One way of doing this is called one of the balloon is this bazooka balloon. It is very popular. What you do, that whatever previously you were doing, apart from that you put another metal sleeve, this outer metal sleeve. You see, inside everything is like the previous one. You have a metal sleeve, and that metal sleeve is shorted to coax outer conductor here. And what is the length of this metal sleeve? Lambda by 4. So, that means it is shorted here. So, at this point it is having an infinite, it is an open circuit. So, it is having an infinite impedance. That means this ZG it is giving, that is infinite. So, that will make I3 very small, and that will try to balance this I1 and I2, because I3 is becoming reduced. This is the bazooka balloon. Now, there is another possibility is, instead of putting that metal sleeve, you can put a another transmission line here of lambda by 4. Here you are shorting as before. Here what you are doing, you are putting that this one, in previous case it was not put anywhere, here you are putting it to the that line 1 or the inner conductor connecting one. So, whatever here it is doing, you see here it is shorted, here it is open. So, that means already the outer conductor and inner conductor, their currents are 180 degree out of phase, you are giving another 180 degree out of phase because of this lambda by 4. So, that makes that whatever current is flowing I 3, the opposite current is flowing in the I 1, and so not opposite, the same current is flowing in I 3. So, again that is making the two balance. This is called lambda by 4 coaxial balance. Now, here you can say that actually this lambda 4, why it was chosen, actually any length of line of this would have done the purpose, but if we do not take lambda by 4, then the antenna operations will be disturbed, because antenna operations have that relation that two currents are 180 degree out of phase. Now, only lambda by 4 can make that. In any other case, the two currents will balance each other, but the operations won't be, that means the inner conductor and outer conductor currents won't be out of phase. And this is, what is this third configuration? So, this one is outer conductor, this is the inner conductor coax, outer conductor. This one, I think this is okay. Now, so Balun, then what it actually his job is now to make this balance to unbalance. This unbalance comes because yes, that I have already said. So, but current flow direction opposite. So, we get a the parallel auxiliary line is yes. So, I think I have said in the Balun. So, this is you see typical, actually you will see in the any VHF, particularly our TV boxes etc., they have that Balun. Without that Balun, actually you do not get a good reception, because the efficiency is poor, because the if the two things are not equal, two currents in differential mode, then actually it appears that there are a lot of noise, because noise also have the same effect, that it makes the equal common mode currents. So, without Balun, actually it becomes that common mode current increases. So, to reduce that, the Balun is used, and if you put the Balun, you will see that the antenna can radiate or receive the current quite efficiently. If you remove the Balun, the antenna won't be, its efficiency will drastically go down, and that you can check, that just remove the Balun and see the reception quality in any TV will be poor, because Balun actually improves the differential mode characteristic. It is something like what we call CMRR in operating a thing, or you will see in EMI EMC people that if you have a multiple transmission lines, then the common mode, if you do not suppress, you will get lot of noise in the or interference in the other ones. So, to reduce that interference, this Balun is used, and it is a problem of high frequency, because we are using coaxial line. So, generally in VHF and also yes, UHF, VHF, this problem, VHF, UHF, TB transmission, this problem is there because coaxial is the medium, but you have a dipole there. We will later see that a design actually the TV antenna was this common mode and differential mode. This current concept was cleverly used to design a actual TV antennas, these VHF TV antennas, which is called folded dipole array, because you see one of the still problem is there that dipole has a radiation resistance of 73 ohm, whereas free space is a radiation resistance of 377 ohm. So, if dipole is directly used to receive, there will be lot of reflection because it is a huge mismatch. So, can we have a dipole, but it will behave as a 377 ohm or 400 ohm radiation resistance? Actually, that problem will be solved by understanding this differential mode and antenna mode concept, but that is for a later lecture. Thank you.